Hello, and welcome to Isabella's explanation of chemistry things. Today we will be completing the following problem. A cold gas surrounds a reaction chamber and absorbs the heat released by the exothermic reaction below. How many grams of carbon dioxide will be produced if 6 grams of octane and 19 grams of oxygen react completely? Calculate the final temperature of the surrounding argon gas if its initial temperature is negative 150 degrees Celsius. Calculate the final pressure of the gas if its initial pressure is 1 atmosphere, assuming the volume remains constant. So down here we have the equation for our reaction and a visual representation of the scenario. This is a lot to take in, so let's make a list of what we're looking for and what information we have according to the problem. We need to find the mass of CO2 produced, we need to find the final temperature of the argon gas, and then the final pressure of the same gas. We know that we have 6 grams of octane, 19 grams of oxygen, and the temperature of the argon gas is negative 150 degrees. The pressure and volume of the gas are 1 atmosphere and 500 liters. This is a combustion reaction, and it is an exothermic process because our reaction is releasing or losing heat. So the first thing we have to do is balance our equation. You can see that there are no coefficients, so it's probably unbalanced. To begin, on the left we have 8 carbon, 18 hydrogen, and 2 oxygen. On the right we have 1 carbon, 2 hydrogen, and 3 oxygen. If we add a coefficient of 8 here, we even out our carbon and hydrogen atoms. And finally, a coefficient of 2 in front of octane, 25 in front of oxygen, 16 in front of carbon dioxide, and 18 in front of water completely balances our equation with 16 carbon, 36 hydrogen, and 50 oxygen on both sides. So here we have our final balanced equation, which might take you a little longer, but I had the answers, so I went through that quickly. The next step is to identify the limiting reagent, with our choices either being the 6 grams of octane or the 19 grams of oxygen. The limiting reagent of an equation is the chemical that, when we perform this equation, we run out of. There just isn't enough to react with all of the other chemical, and we have some of the other chemical left over, so it limits how much we can react. So let's begin by rewriting our balanced equation. We'll write the mass of our given reactants below so we know exactly what we're working with, 6 grams and 19 grams. At this point, we choose one of these chemicals to compare to the other. It doesn't really matter which you choose first, but let's start with octane. We will now find out that if we have 6 grams of octane in this reaction, how much oxygen will we need to react with all of that octane? To do this, we build what's called a picket fence, which you've probably heard of in your chemistry class. We have 6 grams of octane. We know that there are 114.26 grams of octane in every mole of the same chemical, according to the periodic table. We also know that for every 2 moles of octane, we have 25 moles of oxygen. This is something we know by looking at our balanced equation. And we know that in every mole of O2, there are 32 grams, which we also know from looking at the periodic table. So now we can multiply all the top values together and divide them by all the bottom values, and our measurements also cancel out. You should end up with 21 grams of oxygen. This number means that if we had 6 grams of octane in our reaction, we would need 21 grams of oxygen to completely combust that octane. If we look back, we can see that we only have 19 grams of oxygen, in other words, not enough. We'll have octane left over, so oxygen is our limiting reagent. From here on out, every comparison we make will be to oxygen because we have identified it as the limiting reagent of our reaction. Now we have to find the mass of carbon dioxide produced by the reaction. The way we do this is by converting from grams of oxygen, which we already have, to grams of carbon dioxide. If you reference your stoichiometry sheet, you can follow along. We will be converting from grams O2 to moles O2 using molar mass, from moles O2 to moles CO2 using mole ratios, and from moles CO2 to grams CO2, again with molar mass. Before we do all this, let's identify that the molar mass of O2 is 32 grams per mole, and the molar mass of CO2 is 44.01 grams per mole. We can now begin with the first step of calculations, grams oxygen to moles oxygen. We can set up a proportion. If there are 32 grams of oxygen for every mole, as dictated by its molar mass, then how many moles are 19 grams? This is elementary and middle school algebra. You cross-multiply. Hopefully you learn this and remember it. We can multiply 32 and our unknown variable x and 1 and 19, cross-multiplication. We isolate the variable x and end up with 0.594 moles O2. So if there are 32 grams in 1 mole, 19 grams are in 0.594 moles. It's that simple. We'll be using this type of proportion method throughout all of our calculations, so remember this. Next, we need to convert from moles of oxygen to moles of CO2. We can do this by making a proportion and looking at our balanced equation, which I've put up on the screen. If there are 25 moles of oxygen for every 16 moles of carbon dioxide, as dictated by the equation, then how many moles of carbon dioxide are in 0.594 moles of oxygen? Again, cross-multiply and isolate the x, and you should end up with 0.38 moles of carbon dioxide. So in our equation, there are 0.594 moles of oxygen and 0.38 moles of carbon dioxide. Now, the question is asking for the mass of this product, so we need to turn these moles into grams using the molar mass of CO2. If in every mole of CO2 there are 44.01 grams, then how many grams are in 0.38 moles? Perform the same process and we're left with 16.72 grams of CO2. So the answer is that in our reaction, we produce around 17 grams of CO2. The next thing we have to find is the final temperature of the argon gas. The first step in calculating this is to calculate the amount of heat released by the reaction. If you go back and look at the visual representation of this scenario, you can see this chicken scratch of a number here in the corner. This is our heat of reaction. On the top we have a number in kilojoules, which is a measurement of heat. On the bottom we have 1 mole of octane. What this means is that in a reaction, for every mole of octane reacted, we lose this amount of heat. We know this heat is lost because the value is negative. We're losing heat. Heat is being taken away, so it's a subtraction. That's all it is. So if this is the heat for a reaction in which we have 1 mole of octane, how much heat do we lose in our reaction where we have X amount of moles of octane? It's obviously not 1. Well, we're going to have to find how many moles of octane we have. You can make another proportion using the coefficient from the balanced equation, like so. If in every reaction there are 25 moles of oxygen for every 2 moles of octane, then how many moles of octane do we have for 0.594 moles of oxygen? Remember that we calculated our moles of oxygen a few steps ago, so if you cross-multiply and isolate, you should end up with 0.048 moles of octane. In our reaction, this is how much octane we're using. We then set up yet another proportion where we compare the perfect heat of reaction to what we have of octane. If this amount of heat is lost for every 1 mole, then we lose 243.114 kilojoules of heat for 0.048 moles of octane. So this is the amount of heat generated and subsequently lost by the reaction. The next step is to calculate the change in temperature of the argon gas surrounding the reaction chamber. When a reaction occurs and releases heat, the heat goes into the gas, raising its temperature. This is the part where we whip out our handy heat equations. Q equals m times C times delta T, where Q is heat, m is mass, C is specific heat, and delta T is change in temperature. Well, we know our heat is 243 kilojoules. Notice that this value is positive because now we're talking about the argon gas itself, and the gas is gaining the heat. Our mass is 500 liters of argon, or 9.45 moles. Converting to grams using the molar mass of argon, 39.95, you should end up with 1975.5 grams of argon, which we will use as our mass. And the specific heat of argon is 0.5203 joules per grams degrees Celsius. Since our heat is in kilojoules and our specific heat is in joules, we'll convert this to kilojoules per grams of degrees Celsius by dividing this by 1,000, leaving us with 0.000523 kilojoules as our specific heat of argon. Finally, we leave delta T blank because that's what we're looking for, our change in temperature. If you multiply this out and then divide to isolate our variable, you should end up with 236.262 degrees Celsius, the change of temperature of our argon. Alright, but alone this value means nothing. We need to find the final temperature of argon. So this step is fairly easy. To find the final temperature, add the initial and change in temperature together. Remember that our initial temperature was negative 150 degrees Celsius. In the end, you'll have 86.26 degrees, which is the final temperature of our argon gas after the reaction took place. It is also good to find this value in Fahrenheit and Kelvin, so by performing simple conversion calculations, we find that our final temperature is also 187.27 degrees Fahrenheit and 359.41 Kelvin. Finally, we need to figure out the final pressure of the argon gas. For this, we will use Gay-Lussac's law, which states that pressure and temperature are directly related. This is the equation we'll use. Here, we put our initial pressure, 1 atmosphere. We also put our initial temperature in Kelvin, which when converted is 123.15 Kelvin. On the other side, we leave final pressure blank because it's what we're looking for, and we fill in our final temperature with 359.41 Kelvin, which we have from the previous step. Divide both sides and you should end up with 2.92 atmospheres of pressure. So at the end of our reaction, the pressure of the gas went from 1 to 2.92 atmospheres. Awesome. Okay, so final recap of our answers. Our limiting reagent is oxygen. The mass of our desired product, CO2, is 16.772 grams CO2. The heat released by this reaction was 243.114 kilojoules. The temperature change of the argon gas was 236.262 degrees Celsius, and the final temperature was 86.26 degrees. And finally, the final pressure of the argon gas was 2.92 atmospheres. And that concludes today's lesson. I hope you had fun, because I sure did. Alright, see you in the next video. Isabella out.